In any event, we're going to get an update from Bill Beck and his panel, which Bill will introduce. Bill is president of BTM Consulting and has diverse startup general management and technology marketing experience. He has been central to the development and application of laser illumination systems for digital cinema, and I know that's true. I've been working with him for a long time now. Yeah. After 4 years of market and product planning, Bill founded Laser Light Engines in 2008 and co-founded the Laser-Illuminated Projector Association in 2011 to promote the adoption of laser illumination for cinema and other performance projection applications. Bill is currently a private consultant in fiber optics, lasers and sensors, and laser projection. And I think you will all find this extremely interesting. And again, at the end of the session, please leave the glasses on the chairs. Don't leave the room with them. Thank you. Bill.
Good afternoon, everybody, and welcome to the SMPTE LIPA laser session. Laser illuminated projectors, what's new and when will they arrive? The first time I had a chance to speak at this conference was in 2008 as the co-founder of Laser Light Engines. I gave an early talk on the future of laser illumination engines for digital cinema. In retrospect, the audience was justifiably skeptical, but the future is finally here. This afternoon, I have the pleasure of introducing an outstanding panel of fellow laser zealots here to tell you about such things as recent regulatory progress, laser speckle metrology, new laser illuminated projection products, a 6 primary laser 3D demonstration, and a unique opportunity to ask these pioneers and experts questions their presentations will have stimulated. I'll ask the panel to come up and start introductions. We'll begin with a 2-part report by past, well, at this point, Pete is well known to all of us, but past SMPTE president and LIPA founding chairman, Pete Luday. Pete will report first on significant progress LIPA has made on the regulatory front, and then update us on LIPA's work in the area of speckle metrology, an area we all think is critical to the rollout of laser illuminated projection. Pete's a prominent engineering executive in cinema, broadcasting, and digital media. He currently serves as the CTO of Mission Rock Digital in San Fran. Previously, he was Senior VP of Sony's Silicon Valley Research Labs, where his work included just about everything: workflow for digital cinema productions, stereo imaging, and 4K laser projectors. Pete is a frequent speaker, frequent today even, on the future of broadcast, Ultra HD TV, stereoscopic 3D, and laser displays. So let's welcome Pete Luday.
Thank you, sir. And I'll use these microphones if that's okay. Indeed, welcome, and thanks for sticking around after a long day of good information. I'd like to speak today with an update from the Laser Illuminated Projector Association on these 2 topics: updates in regulations, which would make laser projector adoption much easier, and then a little bit about speckle. So first of all, for those of you not familiar, the Laser Illuminated Projector Association, now over 3 years old, has a mission to facilitate the adoption of these sort of new projectors through cooperative industry activities. That means education, safety, training, regulatory affairs. And it's represented by leading projector manufacturers and supply chain companies in all aspects relating to laser projectors. You'll notice that all of the prominent companies in projector manufacturers, laser OEM suppliers, and other stakeholders are included in our current membership. If you don't see your logo up there, you might want to reconsider and join, because this is where all the fun is happening. I'd like to start with a brief overview of what we're talking about when we say laser illuminated projectors. And to do that, I'll compare it against what we're used to using, which is lamp-based optical projectors, optical architecture. You'd have a projector lamp for digital cinema. It would be typically a xenon short arc or perhaps a UHP array. From there, it goes through an optical diffuser and then to the panel, the spatial modulator, usually actually 3 panels, of course, for red, green, and blue primary channels, onto a projector lens in which the image is finally magnified hundreds or even over 1,000 times to get from the innards of the projector to the large projection screen. That's what we've been using for many decades. Let's look at the difference in a full laser-based projector. You'll notice that it's almost the same, but we start out with an array of lasers emitting red, green, and blue light. There's different technologies for the lasers, but they're virtually all semiconductor, often diodes, some with frequency doubling. But from there, it goes to the same sort of light combiner, the optical diffuser, such as a light pipe or fly's eye, then to the spatial modulator and onto the screen. So in other words, all I did is take out the lamp and put in the laser. For that reason, at the left, you'll see the laser, it starts out as laser-type light that has the unique characteristics of a laser, but by the time it emerges from the projector lens, it's virtually indistinguishable from the lamp projector. You really can't tell because of the optical processing. There's one other type of laser projector you'll be hearing about today, and in this case, we start out with an array of only blue lasers. Blue is selected for its optical properties and also its economic properties. Blue laser diodes are very inexpensive because of the mass market and Blu-ray players. I could use them to illuminate a phosphor plate or some sort of substrate that emits a broadband light. A typical phosphor formulation might appear to the eye to be sort of a yellowish white. That combined with a little bit of the direct blue laser creates a very nice broadband palette. And now I've created a broadband laser red, green, blue projector with broadband light, all out of blue lasers, nothing else, creating a light source. Those are often called laser pump phosphor projectors or hybrid projectors. And from a regulatory standpoint, the phosphor portion is known as collateral emissions. It's not the direct radiation of the laser, but rather incidental radiation. And ironically, the regulatory bodies often discourage such things, even though that's the whole purpose for having these sort of projectors. That's one of the hurdles that we're working with in updating regulations. Speaking of which, let's talk about how laser projectors are regulated. As you may know, lasers can be optically hazardous because they concentrate an amazing amount of radiance into a very narrow beam, so that if they happen to get into your eye, for example, they could concentrate all that photon energy, all those watts, into just a few retinal cells and burn them up. That's not a good thing. So, but in the course of laser projectors, as we said, they're really changed. However, let's talk about the way the FDA views it, which is the federal agency in the US which regulates lasers. I always wondered whether a laser is a food or a drug. We will never know the answer to that, but life goes on. They've created this wonderfully named section of federal regulation called the 21 CFR 1040.10 and 11 that describes lasers and the safety configurations. There's many aspects, but bottom line is that these federal regulations in existence for many years aren't really harmonized with worldwide standards. They make no distinction about how the laser light is finally emitted from a device. Nobody really thought of a laser projector at the time these regulations were made. So subsequently, in the early 2000s, they created something called a laser notice, published by the FDA, updated for the last time in 2007. And this provided guidance to the industry to conform to certain standards. It said, although our laws are a little bit inappropriate, hard to read, and unharmonized, if you'd prefer, please use the updated IEC regulations out of the global European body, and that'll be fine instead. So it gave permission to use the IEC global regulations in lieu of the 1040, 21 CFR 1040.10 and 11, and that's served us very well for these years, except when you get to bright laser projectors, which fall under this thing called a demonstration laser product. If it's rated as a class 3B or 4 device, because it has that much optical emissions coming from the lens, even though it has nothing to do with laser light, you have to get a special permission to use it, otherwise it's illegal. that special permission is called a laser light show variance. It's a big old form. You can find it on the FDA website. You might notice on the little check marks they say, is this a discotheque or a trade show that you're trying to use this thing for? How many days? How many operators? This is not exactly appropriate for a theatrical environment. These laser light show variances have a duration of 3 to 5 years, and they have to be renewed if the manufacturer applies for that. Many other points. So you could certainly use laser projectors today of very high brightness. You have more paperwork to do, and we think that's not a good long-term solution. It's too burdensome, and if you look at the uptake of laser projectors, especially some of the mid-range laser pump phosphor units, not just for theatrical, but for churches and meeting rooms, and even FDA conference rooms, they need some. There'd be many variances if these laws weren't changed. Now, besides that, each US state has the ability to create their own laser regulations. LIPA conducted a thorough investigation with the help of a very skilled law firm in Washington, D.C. to assess this, and here's the results. You'll see that there's about 6 states. The green states really don't have any laws that would be horribly burdensome. The yellow ones have some rules that need to be addressed, and the 5 states in red, like Texas and Arizona, Florida, New York, Illinois, have specific regulations that really do need to be addressed. In some cases, if the FDA would change their rules, then these would automatically ripple through, in some cases not, and we need to work on that, just to give you a flavor. But the most important thing here is what's happening at the IEC in Geneva. That's the regulatory standards body, really, for international standards that's adopted by much of the world, including by proxy from the USA, FDA. Now, the IEC rates all laser devices under what they call 60825. And Chapter 1 defines what lasers are. It covers medical, industrial, laboratory use, laser welding devices, military weapons, as well as laser-illuminated projectors. It was last updated in 2007. It was called Edition 2. Now, subsequent to that, the technical committee within IEC recognized the need for updating and spent the last 2 years working very carefully to redefine the parameters that really make a laser subject to laser regulation. And in that process, all the countries participating in IEC, which is virtually all the advanced countries in the world, have come up with a due process, open ballots in order to come up with a new rule, the result of which the laser illuminated projector emissions would be treated under LAMP regulations, not under laser regulations, which is appropriate because they're no more dangerous or no more distinguished than LAMP projectors. Breaking news, just 3 weeks ago, the IEC approved, after over 2 years of effort, the new Edition 3. And this is to be published as a formal international standard by IEC. It'll be called 60825 Edition 3 as of the end of this month. That's a good step in the right direction. What does that mean? It means that under the 60825 Edition 3, laser projectors, as shown there, will be carved out and moved over to a set of regulations that is appropriate for LAMP devices. The threshold is a carve-out measured in radians at about 1 megawatt per square meter steradian over alpha. I don't expect you to know what that means. It's really complicated. But it means that virtually any laser projector up to maybe 100,000 lumens would be treated as a LAMP. Further, IEC is now working on what's called the -5 vertical standard, which will specifically address regulations for LAMP systems of image projectors, including both LAMP and laser. And that's expected within the next year. Much work remains. The FDA must adopt this IEC standard. The EU regulatory bodies must also adopt the standard, have to deal with United States state measures, as well as people like OSHA, FAA, and many others. So LIPA will be busy. If you want to help, please join LIPA. Our executive director put it very nicely. She said the risk of failure or delay means that much higher costs for every company involved in laser projectors, having to meet the extra reporting and regulatory requirements. The investment in a LIPA membership could pay off huge dividends in terms of being able to move forward, join the industry coalition. Now, I'd like to talk briefly about one other topic, which is laser speckle. This is an undesirable attribute caused by the coherence of laser light. Everybody has seen it, that shimmer on the screen. It's an interference pattern caused by the coherent light. It's visible when light bounces off the screen, and it's measured by what's called speckle contrast ratio, which is the standard deviation of brightness divided by the mean intensity of brightness. It's between 0 and 1 or 0 and 100. The kind of speckle that we're talking about needs to be below 5, maybe even below 2%. The problem is that while laser projectors are of great interest, there's really no consensus methodology on how laser speckles should be measured. There's lots of good work that's been going on, different opinions about it, but the truth is it's rather relatively complicated. And so the LIPA board last year created the LIPA Laser Speckle Metrology Working Group, which I'm honored to chair. Work started last year. There's 20 working group members who represent all the experts in the field. And the goal is being to achieve a consensus on the measurement methods to assess laser speckle on these projector devices. And good progress has been made. First of all, and I'll run through this very quickly because further details will require a long time in a future conference. But when you measure speckle, you start out with a laser device that started as pictured at the top. You'd probably have a reference laser device that has a known amount of speckle, goes through a lens and onto a reflective surface such as a screen. Then you photograph it with a still camera to assess its mean versus standard deviation intensity. But there's many factors. The reference light source, some good work by laser light engines and CQ lasers have defined for us what might be an easy to build reference laser device to meet those initial needs. Now the camera is a critical part. There's so many factors listed here: the clear aperture, the focal length, pixel size, focus point. And that has been addressed by the metrology committee with many hours of discussion, debate, exchanging of information. Here's one interesting point about the size of the pixel, and I will attribute the research here to Barco. If you see on the top picture, the wavy line represents a speckle going from dark to light as you scan it horizontally across the screen. And if you have a tiny pixel, as shown at the top, your C1, the red vertical line, is showing you what the intensity measurement would be. If your pixel size is larger, then your measurement would be in the bottom graph C2, and it would understate the amount of speckle. How do you correlate that to human vision? It's difficult. Here's a couple of the types of cameras that have been used: a CMOS with 2.2 micron or a CCD with 6.4. There's been lots of tests to be able to understand the benefits of those. Secondly, is any image processing allowed? Gamma, what's the exposure or integration time? Those things need to be determined. The nature of the screen reflective surface has a big impact. That needs to be defined, as does the room geometry. How far the camera is from the screen will influence the type of speckle measurement, some cases more than others, depending on the speckle mitigation techniques that are used. Here's some examples. RealD contributed some good new data having to do with the apparent speckle versus viewing distance. And it's not just the visual acuity of the eye, it has to do with the geometry of the speckle going through your iris at 3 millimeters and hitting the retinal cells at a certain angle. And here's another example of new research, this one contributed by Harton Screens. This has to do with how much you could crop the image on the screen and still ascertain the amount of speckle if you're looking at just a portion. Many other complicated factors, but here's an interesting one, and this was contributed by Christie Digital. You'll see here that there's 3 bars, and there's 9 different screens that were measured here. Left to right, labeled 1 through 9, and each of them has 3 measurements. The blue line is looking at one type of camera that happened to be a CCD. The red line is the CMOS camera, and the green line is humans that were observing this and reporting back. And you can see that there's different correlations between different cameras and what viewers see. Much more work remains. So there's general agreement on these points: the general light source, camera processing, and screen geometry. Still open discussions about the camera to be used, and the next steps really that although we have good parameters now, work remains, and we'll be working on completing a detail of everything I've been talking about over the next few months, hopefully in June timeframe, and we welcome any participation or questions or LIPA membership. Thank you very much.
Before we leave this topic, I want to extend a my personal appreciation to Pete for the work he's done founding LIPA. We're going to see some very nice laser projection today, but without the work that's been going on in background, and I grant you all that it's a little bit dry, but that late-breaking news from the IEC is probably the most significant news about laser projection we've heard in a very long time. So thank you for the great work you've been doing, and thanks to all the supporters at LIPA. Okay, our next speaker is Dr. Goran Stojmenovik. He's the product manager for laser projection at Barco. Goran's talk is entitled RGB Laser Technology for Premium Cinema Screens. Goran's been at Barco since 2005. In addition to his leadership role in Barco's laser projection development for cinema, he also has experience in post-production, LCD monitors, control rooms, and broadcast applications, so he's a well-rounded guy. Goran has a PhD in engineering physics from Ghent University and resides in Belgium. He came over yesterday specifically to give this talk. So please welcome Dr. Goran Stojmenovik.
Thank you, Bill. I'm actually lucky to be here because I have a 3-week-old daughter back in Belgium that was born 2 weeks ahead of time. She's all fine, but just about old enough for me to escape and come to Las Vegas. Unfortunately, flying over 9 time zones and being in Vegas is not going to help me catch up on my sleep deprivation, so please be kind. Okay, so having my daughter is a wonderful experience, of course. It also means that I missed CinemaCon, and a lot of you will probably know what, maybe through press releases or have been there, what Barco has done at around CinemaCon. We have launched our high brightness direct RGB laser illuminated projector, and I will actually want to start with a wrap-up of that show. So we had a first public showing of our, as we call it, DP 4K 60L projector. I leave it to you to figure out what the numbers mean. We are showing it still at a Cinemark XD auditorium at South Point, probably 10 miles south of a bit more here in Las Vegas, on a 45 feet wide screen with a gain of 1.8. Among other things, we're also screening the Hobbit 2 trailer at 14 foot Lamberts, 3D with a single projector, 6P color-based 3D. And around the same time at CinemaCon, we also made some announcements of commercial sales, actual projectors that are going into the market, among others, Cinemark, 5 projectors, Santikos in San Antonio in Texas, Kinepolis Group in Belgium and the rest of Europe, and a number of projectors in China. And I'm sure there are a lot more to come. The point here is that we are excited about this thing as much as the exhibition community is. And finally, for us, after many years of research, we see that there is appreciation for the laser illuminated projector, and they're finally hitting the market. Now, you might have asked how Barco is involved in laser projection, because probably in 2013 there haven't been much announcement from us. The fact is that as a projector company, we are into the laser projection R&D development for many years now, before 2010. And for us, this has been a journey. It has been a journey not only in understanding how to make a laser projector, and then going through several prototypes, a 300 lumen LCOS, a 3000 lumen wavelength diversity testbed 1, as we call it, testbed 2, which has 55 or 56,000 lumen that we showed in 2012, testbed 3, and then final release. So it has been a journey with several technological improvements, but also one way where we actually had and maintained close contact with the cinema community, with post houses, studios, and post-production professionals around the world. I will not go into detail here. You'll probably have the chance to look at it now. My intention was, before going to the next slide, to show what laser projection different models of laser projection, but Pete explained that pretty good and with nice slides. What struck me actually is that on the flight from Belgium to here, actually a person, we talked and a person told me, oh, so we're actually shooting laser beams over the audience's head? Said, no, this is not what we're doing. And this is the whole message. There is no laser beam shooting over your head. It's light coming out of the projector as it would be from any lamp-based projector. Just very briefly, laser phosphor solution combining phosphor, excited light from phosphor with a blue laser and a direct laser, red, green, and blue lasers, which are then combined to form an image on the imaging chip, and light is coming out of the lens. At this moment in time, there is a huge difference in this technology, not only technology, but in performance. At this moment in time, laser phosphor projectors only reach about 6,000 DCI lumens, while the direct RGB projectors are reaching 60,000 lumens, potentially even more. So, two different market spaces, two different technologies. And I'm going to talk about the direct RGB illuminated projector. In our journey, as you said, developing, researching laser technology, but also having contact with studios and with post-production communities, and with our large installed base of exhibitors. What we realized is that for exhibitors mainly, there are two different topics which are of prime concern if they're in the prime cinema business. One of them is the audience experience. And I'm not saying laser is going to show it, I'm not saying high frame rate is going to solve it, but specifically specifically for lasers, there is laser-based projectors. They bring a promise of brighter 3D. Why? Because they're brighter projectors, because they offer better 3D efficiency, and so on and so on. Today, dark 3D is one of the biggest pains for the exhibition community. Not only that, laser projectors also offer better, or promise of better contrast, uniformity, sharpness, and color gamut, and so on. Not only the image, the experience is higher, also it's more consistent. You don't have lamps. You don't have a situation where you go 3 weeks from now to the same cinema and suddenly your screen is much darker than it was 3 weeks back. The experience is always the same and consistent throughout years. Next to that, laser illuminated technology also provides an opportunity to have a low total cost of ownership for the exhibitors. There are no lamps. You don't need to plan for them, to buy them, to stock them, to replace them, to dispose them because they have hazardous material. You don't need to worry if the lamp explodes, about the warranty claims with the lamp supplier, about the cleaning of your lamp house or projector, and so on and so on. Set it and forget it. It's there for many years to come. Also, there is a better efficiency in terms of lumen per watt performance versus xenon, and I'm going to talk about that later. Of course, there are challenges, and Pete spoke about them: regulatory, speckle, one of the prime challenges in image quality, and cost. But the reason people are buying laser projection now is not only because of total cost of ownership. They want to save money. Yes, that's a really nice given. The reason is elevating the exhibitor experience or the visitor experience to a higher level. Now, Barco approach, having all these things in mind, is to actually focus on those two things. So for us, the laser illuminated projector should be better, should be same or better than xenon. And several areas, this better than, we interpret it as providing a higher brightness, focus on speckle removal, sharpness uniformity improvement, and improving the efficiency with 6P based color 3D. The minimization of OpEx, and that's a second but not less important focus area for us, means that, for example, we're conditioning the laser, the diodes, their working temperature, humidity, and so on, to expand their lifetime to a very, very, very long range. And we also try to minimize the losses, the optical losses of the laser technology by, for example, avoiding use of fibers in our system. This leads me to the Barco product concept, which is, as you can see in this very raw schematic, it's an integrated projector. All the laser diodes, the laser light source is integrated inside one projector. We call it direct coupling. So we're not using a fiber, any fiber solution. This direct coupled approach increases the lumen output for the same wattage applied to the system. In order to increase the lifetime, we have an active cooling. So there is an external chilling element that extends the lifetime of the DMD and the laser diodes. And a unique feature there is that we have a 6P, a 6 primary in a single projector. So single projector can provide you color-based 3D without dual projection installation, maintenance, and service. Last but not least, of course, we have a proprietary despeckling, which if you join our demonstration on Sunday evening, and you'll get cards at the back or tickets, you'll see what it means in real cinema terms. The product that we have and that we launched at CinemaCon, it's a picture of it. It comes with performance of up to 60,000 DCI lumens. It offers 30,000 hours of lifetime, and it's important one because there is only 80% remaining light. Not only 20% decrease, but as much as 80% remaining light after this lifetime of the light source. It has the active 6P. We dubbed it Barco Laser 3D technology because it's the unique one in its kind to be integrated in a single projector. And integrating projector electronics with our new media server, it offers a possibility of 4K 60 frames per second and 4K 3D with the same projector. Now I will jump through a couple of topics briefly that explain the technology behind the projector. 6P is a big word. It's been around maybe for a couple of years. It's basically color-based 3D, color separation per eye. And with lasers, you don't need a color wheel. You just do the separation by choosing the right wavelengths. So, of course, you need special glasses, but the result of that is that the 3D is crisp. It has a very high extinction ratio of probably 1,000 to 1 or even higher. And the 3D efficiency is twice higher than with the Xenon projector and Dolby today. Coming close to real DXL, not quite, but still a couple of percent to go. And there are no silver screens needed, and you'll all know that a silver screen provides, at this moment, still less reflectivity back to the audience. So in total, the total reflectivity of the screen, and you have a hot spot and so on. The lifetime focus and TCO, it's a typical graph where you have the lamp, 500 hours lifetime of 6.5 kilowatt lamp. The message I'm trying to give here is that if you have a projector that has 20,000 lumen, 20,000 hours lifetime, and another projector that has a 30,000 hour lifetime performance, what's really important is to know what is the brightness, the remaining brightness at the end of this lifetime, because it's not only a factor of 1.5 in lifetime differences, it can be up to a factor of 4 to a similar performance. Speckle. Pete also explained a bit, what speckle is, what the metrology is, and so on. At this moment, there is no universal accepted way of speckle measurement, but Barco has a long history in speckle measurement and research and so on, going back to 2010 to the papers that we published by the so-called Mr. Speckle. You'll know who that is. What I'm showing here is a couple of percentages which probably don't mean too much because they're relative, but we started with a speckle performance, speckle contrast ratio of 16%, and then going down over different iterations to something which is today at 2%. So huge improvement in speckle just by doing the projector, not doing anything external, in the ecosystem around it. 2 slides to finish with data, a lumen per watt comparison of our laser projector to our Xenon projector. The point is, when you have a Xenon projector, it always consumes the same electricity, but at start it produces most lumens, and then after 200 hours it's probably down to 75% and so on. So if you see the comparison of a 7.5 kilowatt projector that produces 33,000 lumens in the beginning, or maybe 25,000 lumens after a couple of hundred hours, you see increase of wall plug efficiency with our system. Worth 36% better or 63% better if you compare on average light level. So yes, OpEx reduction is a fact with the laser projection. It's not only a question of higher brightness and premium screens, but it's a reality for exhibitors as well. And application examples of the single DP 4K 60L projector with 60,000 lumens. One projector can light up screens in 7-foot Lambert 3D and 1.8 gain up to 24-meter screens. Or if you choose to go to 14-foot Lamberts, your screen size is reduced to 17. The message I'm trying to give here is that with a single projector, there is a single projector can provide 7-foot Lambert, which is today's DCI high frame rate 3D recommendation, to almost any premium screen in the world. I'll finish by inviting you all to our screening of, you probably have heard, we have an integrated cinema at South Point at the Cinemark XD Theater. Cinema with the escape, with the screens on the side, audience entertainment and so on, but also with laser projection. We're doing 2 screenings, a more technical one tomorrow evening at 6:30 and a more general one, which is basically a copy of what happened at CinemaCon on Monday evening at 6:30. And you can get tickets at the back. Thank you very much.
Yeah. Thank you, Goran. And if we go back to the title of this session, What's New? Certainly commercial sales of laser projectors and multiple installations this year is new, and it pays off the question, when will they arrive? Another new technology, different technology we're going to talk about now. Our next speaker is Rich McPherson, Senior Product Manager for Projectors at NEC Display Solutions. Rich will introduce a new technology and a new product in the cinema world. The first commercial laser cinema projector based on blue laser pumped phosphor technology, or BPP as I call it, blue pump phosphor. Rich has been with NEC since 1995 and in projection for over 25 years. He has guided NEC's digital cinema rollout and now is managing the introduction of their laser-illuminated projector offering. He's responsible for marketing, product roadmaps, messaging, and new product introductions. Rich holds dual degrees in electrical and mechanical engineering technology from Corning Community College. Please welcome Rich McPherson of NEC Display Solutions.
Thank you, Bill. So I'm going to tackle this a little bit different than we've already talked about concerning laser projectors. NEC has a laser projector that is a fiber system that we demonstrated last year as well, but this year we've taken it into a different realm and bringing in a laser phosphor projector. We're trying to look at the market with different dynamics. We know that certain manufacturers are taking it and looking at the premium experience. When we say premium experience, those 55, 60, 65-foot screens. NEC is kind of looking at it as taking it from the 20, 25, 30, 35-foot screens. That there's a majority of screens out there that need some technology in this realm, like laser, to promote in that regard. So that's what we're really looking at. So what we're introducing is what we consider the world's first fully integrated compact laser projector that is DCI compliant. This is the world's first one. It's a 3R system. And the reason it's a 3R system, I'll show you a little bit later on with the drawing of the projector itself, but we are able to achieve that, one, because of the blue laser and the phosphor-based system, but also because of basically a shroud around the lens that helps us make it a 3R system. Screen coverage is 36-foot wide image, which is 11 meters, but it's 14-foot Lamberts, so we can achieve 14-foot Lamberts in 2D, not 3D, and it's on a 1.8 gain screen. The laser light source itself at maximum brightness achieves 20,000 hours of life. Goran kind of showed a little bit of a map for that as well, and that's what everybody's going to achieve in this realm. Complete DC solution, so It is a complete system with lens, projector, as well as the IMS built into the system. It is released in May, will be released in May. Actually, we announced it. Manufacturing has begun. We will receive units in April. We will start shipping in May. Why do we really want to talk about laser? Why is it important to the market, to our customers, to the viewing audience? Highly reliable. We do not have to worry about lamps failing or lamps exploding or lamp cost. So that's the biggest thing that we look at, as well as the degradation of lamp technology in the immediate release of the film, the immediate release of that lamp onto the market. Within a few hundred hours, as everybody knows, those lamps start to go darker. With laser, that doesn't happen. It stays linear for a long period of time. High redundancy. What we're referring to here is the fact that because it's not a single laser in the projector, it's multiple. In our case, it's 100 plus lasers. We have redundancy built into the system so that should a laser or two fail, the system will automatically compensate itself to keep that brightness up to the DCI spec. So we don't have to worry about that scenario. One thing I don't have up here is also the uniformity. So we're looking at brightness uniformity and white uniformity across the screen. As you know, traditionally with lamp-based technology, you do not get a perfect white or brightness across the screen. With laser, we're able to do that, whether it's laser phosphor or laser, or direct laser, you are able to achieve a better balance across the screen. So that's another advantage that I didn't actually put in the slide. One thing there I talked about was the remaining LDs, what we consider laser diodes, compensating. The system not only looks at it from a brightness standpoint, but it also looks at it from a color balance standpoint. So we're looking at each individual laser that goes out and how we're going to compensate. So there's a feedback loop coming in, and I'll talk to that on another slide. Dramatic savings. Goran talked about this, but really what it really comes down to is that anybody that's been purchasing lamp xenon-based or UHP-based projectors, which NEC is one of those companies, lamps fail. Lamps have to be replaced every few hundred hours, or in some cases, 1,000 hours, or some cases 2,000 hours. Here I have 1,500 hours of 3,500 hours. That's because in the realm that we're playing with this particular projector, they're only usually a 1.5 to 2 kilowatt lamp, so the lamp hours are longer. In the realm that Christy and Barco are talking about, those lamps are much less efficient, and they're gonna go down a lot sooner. So we can say it's 1,500 to 3,500 hours in this realm just because it is strictly a much lower wattage product. But we don't have to worry about lamp replacements. We don't have to worry about the explosions again. And then, of course, when we say storage savings, realistically, you're looking at the fact that customers, when they purchase a lamp or a projector, they don't have to purchase extra lamps, keep them in stock, have carrying costs. They don't have to worry about lamp explosions. Again, that's a big word, but that's one of those things that they don't have to worry about. With the laser projector, you don't have to do that. You simply buy the product. We'll have a laser module that will be also available from a service side should something really catastrophic happen, but we'll be able to handle that at a later date. But we don't have to worry about that up front. Just some specifications. In our case, it's a 2K projector. It is not a 4K projector. I'm not going to read all those specs because I can't see the monitor, and I don't think you can all read those exactly either. But the point being that it is a self-contained system that is realistically about 136 pounds. So the advantage to that projector is I can mount it in the theater, I can mount it in a projection room, I can mount it upside down. It doesn't matter to us how we want to mount it. We can do all that within that little tiny projector system. So really, what is it? It's a blue laser with red and green light derived from the yellow phosphor. So as you can see here, we're saying green and red light are derived from the yellow phosphor. The blue laser excites that phosphor. You get basically a white light with the blue and yellow together. That's then going out to the optics. And then we derive the red, green, and blue going into the 3 different DLPs itself. So there's an optical splitter that everybody uses from this standpoint, that we split the red, green, and blue and make white light out front. High power solution. Yellow phosphor is suitable for higher power excitation. So really what we're referring to here is, in the past there has been, up to this point, there actually has been some manufacturers that use laser LED-based light sources, and also use green phosphor so that they derive different light from that. Well, the green phosphor doesn't have the characteristics that we need or the ability to handle the extreme heat or the power coming from the laser for the projector. So we use the yellow phosphor to also help in that regard. Red emission is saturated if we use the red phosphor, so the red emission ultimately gets really oversaturated. So we're driving the red too hard. So with the yellow phosphor instead, we don't get that overdriven red. So we can keep our colors in control and not oversaturated. It's less expensive. Of course, it's less expensive than a 3 RGB laser system. That's because we're only using the blue light and the blue laser. And as it was talked about earlier, it's much cheaper because there's so many more blue lasers on the market. The other real big advantage in what we did at CinemaCon different, and it's not on the slides again, but what we did different at CinemaCon, day to day, we actually put a silver screen up and we put a white screen up. And the reason that we did so is because with the laser phosphor projector, that bad word that everybody's talking about, speckle, really doesn't exist. So we took that chance and we showed customers, we were fairly confident we were doing the right thing, and we showed customers speckle, or a speckle-free projector image on a 1.8 gain, or actually a 2.2 gain silver screen. Downside there was some hot spotting, of course, especially in the situation we were in, the room we were in, but we proved a point that you can remove the speckle when you're using a laser projector. So that was one of the things we did at the CinemaCon altogether. Then, of course, as I said, less expensive. Most current high-power green lasers are using a SHG technique, and then the SHG laser is expensive as well, so, and it's with a lower efficiency. So just for this type of product, at the price point we're looking at, we wanted to do that hybrid system. Compact light source module, implementing of the blue laser for the phosphor, blue laser for the blue light, and then yellow phosphor diffuser, etc. And then you can see on the bottom, it's a class 3R system. Only blue output laser is coherent portion of the entire spectrum. The red and green are not coherent, as well as the red and green are actually broadband light, where the blue is not, just because it's a blue phosphor. Short throw distance, and then of course 3R with the laser hood. So there's the image that I was talking about. I would show you is we're actually achieving a 3R system by putting about an 8-inch hood on the front of the projector, but that allows us to sell this projector immediately without any of the variances that we talked about earlier. Liquid cooling for the system. So yes, even in this scenario, we use liquid cooling as everybody else will for their laser diodes, as well as the DMD, but we use liquid cooling for that. And then it's a high-powered, high-efficiency phosphor material, low thermal quenching, optimal phosphor excitation, so optimal spot size, and then DCI color space, which of course that's the ultimate goal, is to have a DCI color space with the projector itself. Dynamic self-adjustment light mode. So this is what I alluded to earlier, but it's really what's most important, I think, in this realm. If we look at the fact that the projector today, projectors with xenon or UHP, if the lamp fails, the show goes down. You don't have very happy customers. So with this system, and with a 3 laser system, direct laser system, you have multiple lasers that will compensate for the system. So should something happen, red, green, and blue will stay there. You'll have the same brightness. You'll have the same DCI color space. Nothing else will change. So all we're showing here is the fact that you won't have to worry about that as well. And because of the fact that on the left-hand side, the bottom left two images, because the phosphor and the blue laser change a little bit over time, we're able to compensate electronically, manipulating the laser and the phosphor, the light coming into the phosphor, to make sure that the colors stay consistent. This is just an image of the projector itself. So as you can see, we have that about 8-inch shroud on the front of the unit so that we can make sure that we stay 3R, but that allows us to sell the projector in today's market. So again, we'll start selling this in May, and we had a very good reception at CinemaCon, so it looks like we'll start moving in that direction. That's all I had for now, so I can't read most of those words, but thank you very much. Thought I covered most of the crowd.
Thanks, Rich. And I think that's a very clever and important development in the solid-state illumination world, and glad to see also commercial product introductions this year. Our final speaker is Dr. Don Shaw. He's Senior Director of Product Management for Christie's Entertainment Solutions. Don will present Christie's new dual projector Laser 6 primary 3D system, and will follow up his technical presentation with a demonstration of the system with a variety of cinema content. And as you've seen in the back, the tower back there has got on top of it a pair of Christie 4K projectors, and they'll be used for the laser projection 3D demonstration. Don leads a team of product managers that works with global customers, partners, and the Christie engineering team to develop new products, including laser-illuminated projectors. Dr. Shaw earned his PhD in computer engineering from the Royal Military College of Canada and has published numerous technical papers in electronics and semiconductor technology. He's developed expertise in video processing and image quality for cinema, high-end home theater, and broadcast quality video display equipment. Please welcome Dr. Don Shaw of Christie Digital Systems.
Thanks, Bill. Good afternoon, everyone. It seems I have the distinction of presenting the last PowerPoint of the day, so I'll go through my slides as quickly as I can. Today I'm going to be talking to you about 6 primary laser projection. But before I do that, I'd like to address one point that I think is very important to everyone in this room, is the market need. Why are we building laser projectors? And it's not because we can or because the other guys are. It's because there's a well-established market need that we're trying to fill with this type of product. And that's in the premium large format theater space, but more specifically, it's in the 3D space. I think you could argue that 3D has had a tremendous impact, a positive impact on the cinema business. For one thing, it gives people a darn good reason to see films at movie theaters, despite a plethora of other options for consuming content at home on their 70-inch LCD or on their iPad or their mobile phone. The only place you can get a truly immersive 3D experience is at the local movie theater. Of benefit to most people in this room as well is that you could argue that 3D has driven the rapid adoption of D-cinema. Back in 2009, a film called Avatar was released, and exhibitors realized, hey, if I want to show this film the way James Cameron intended it to be seen, I need to put in a digital cinema projector. I think the most important thing to the industry in general is that 3D films, 3D movies, allow a significant upcharge at the box office. But the picture's not all that rosy. If we look at the 3D take rate in a domestic market, so in the US market here mostly, you can see that the actual number of people who choose to see a 3D film on opening weekend versus the same film in 2D is declining dramatically. For instance, in 2009, if you released a 3D film, you could expect 67% of people to choose the 3D version of that film as opposed to the 2D version. Now fast forward to 2013, and you can see that number's dropped to 42%. Now this is a phenomenon it's pretty localized to the domestic market, but certainly it's going to happen in international markets as well once the novelty wears off, unless we can do something about this as an industry. So first of all, let's look at what the problems are. If we look at a study done about 2 years ago, published in the Journal of American Academy of Optometry, they report that yes, 3D heightens the perceived sense of immersion, but it also has some physiological effects that go along with it. Blurred double vision, dizziness, disorientation, nausea, motion sickness. Who's going to pay a premium for an experience that's going to offer these types of physiological side effects? Of course, I think everyone in this room will agree the biggest problem is brightness on screen. Showing a 3D film at 3 or 4 foot lamberts is not ideal. All of your critical details hide in the background. All the scenes look dark and murky. It affects your ability to perceive the colors correctly. I like to make the analogy of dim 3D to reading in the dark. You know how your mother always said, don't read in the dark, it's going to make you go blind. Well, probably not, but it's going to give you eye strain. It's going to cause headaches in some people. It's certainly not a comfortable experience. So this is the first area that we need to address. But beyond that, there's other things. I think we have to look at stereopsis as well. And stereopsis is our vision process whereby we take in two images at once, two slightly offset images as shown in the picture there, and we reconstruct these images together as one as our primary means of depth perception, along with other cues such as surface textures and relative sizes. But the important point is that stereopsis is a naturally simultaneous process. When you go to a cinema today, 99.99% of the time, you're seeing 3D as an alternating left and right eye image. That's not natural. You don't go through life alternating your left and right eye when you're viewing objects. We believe this is an unnatural visual effect. It contributes to some of the uncomfortable physiological effects that people have when they're watching 3D films. It exacerbates motion artifacts on screen. Certainly, we believe there's a strong preference for simultaneous left and right eye images in a 3D presentation. Some other things to look at. Crosstalk. Some companies call this ghosting, and that's where you see an extra edge around images. The fit of the glasses. They have to be comfortable. They have to fit over your existing eyewear. They have to fit different size heads from children through to adults. System efficiency. Of course, we've talked about brightness. We want our 3D images to be as bright as possible. So that means they have to be as efficient as possible. And I'm probably going to be the first one today to make a real rant on conventional silver screens. There's tens of thousands of silver screens installed in cinemas around the world, and we're not doing anyone a favor by showing them a film on a silver screen. For one thing, it's an extremely non-uniform experience, which is extremely unnatural. But more so, that non-uniformity means that the audience is getting a non-uniform experience. Sure, the people in the middle, they get a hot spot, a bright spot right in the middle, and that's all right, because that's where most of the action's going on. But the people over on the sides of the theaters, they get their hot spot, the bottom right corner, bottom left corner of the screen. There's nothing going on there. The rest of the screen is virtually dark to them. So beyond the non-uniform experience, silver screens, as the other panelists have already indicated, exacerbate this speckle artifact that you see with laser projection. So putting this all together, we've created a model of a premium 3D experience with, of course, the foundation being great content. As a manufacturer, there's not a lot we can do about that, but certainly there are people in this room that can help out there. But on the projection side, we can build projection systems that are very high contrast. We can build high brightness projection systems. We can put in systems that use low gain white screens as opposed to non-uniform silver screens. We can build projection systems that offer simultaneous left and right eye images. Of course, some other primary building blocks. Resolution. We've heard all about high resolution today in 4K versus 2K. Higher frame rates. Crosstalk between eyes. All things we need to look at. On the operational side of things, energy efficiency, glasses comfort, friendly business model. So let's talk about laser projection as a solution for these things. Up until CinemaCon of this year, every laser demo you've seen was probably something called a 3 primary laser projection, with the exception of the laser phosphor systems. And what 3 primary means is that the light source is being made up of 3 laser primary colors, a red, a green, and a blue. And we've shown that you can pump a 3P laser system, you can pump 72,000 lumens through a single projection head. In fact, we had a demo last year at the AMC Burbank where we ran a full commercial run, 2.5 weeks, pumping 72,000 lumens through a single projection head without any failures, no smoke, nothing was on fire. A great learning experience for us. But beyond brightness, we've also talked about laser projectors having this much higher color gamut. Once the industry figures out how to take advantage of that, we can build higher contrast systems. With a laser projector, you can trade brightness for contrast, and we're going to show you an example of that today as well. The other speakers have talked about the efficiencies of no lamp changes. Talking specifically about a 3 primary laser system, it'll work with most 3D systems except for color separation-based 3D, i.e. Dolby 3D, and this is an important point. I'm going to come back to this. But overall, we think that 3 primary laser is certainly a better 3D experience than anything you can achieve with a xenon-based cinema projector. So before I move on and talk about 6P laser, I'd like to pause for a moment and talk about the current state of cinema 3D systems, because this is really what we're trying to optimize with 6P here, is the 3D film experience. And I've broken the systems roughly down into 2 categories, those which require a silver screen for polarization preservation, and those which work on a white screen. So perhaps the most common system out there is something we refer to as a light doubler. This is by far the brightest solution available today, coming in at about 27% efficient. Real D has a huge market share here, over 15,000 XL screens installed worldwide. Also on the silver screen side, there's a system that's based on a big spinning polarizing wheel in front of the projector. And that comes in around 16% efficient. We've seen systems, dual projection systems, that use static polarizing glass as their means of achieving 3D. Now this is really high quality 3D, but again, it's hampered by this low efficiency rating, 16%. And when I give you an efficiency rating on this slide, that means if it's a 16% efficiency, that means that's the light leaving the project. Only 16% of the light that leaves the projection lens actually makes it back to the viewer's eyes. Another common technology on this side is your simple liquid crystal polarization modulator, and that's a little screen hanging in front of the projection lens. Everyone's seen those. There's a lot of players in this space. Over on the white screen side, there's really only two solutions for doing 3D on the white screen right now. Oh, big X there. We don't like silver screens. First one is shutter glasses. Those are those big red glasses you've seen in some movie theaters. They come in at about 13% efficiency. And the way these work is they modulate the left and right eyes, shutting them off and on. I can't stand wearing them for 2 hours because I see a flicker effect in addition to the strobing effects on the screen. The glasses are quite pricey compared to the disposable glasses. For instance, if you're paying $30, $35 a pair for a pair of shuttered glasses, someone comes in your movie theater, spends $10 on a movie ticket, and walks out with your $35 pair of glasses, you're not doing very good business that day. But I think more importantly is based on an estimate that any given time, 10% of those glasses will have a dead battery. So that means if someone comes into your movie theater, you give them a pair of shuttered glasses with a dead battery, they put them on their head, they start watching the film, they don't know what's wrong. All they know is 3D sucks. We've lost that person. The industry has lost that person to 3D. Final system is based on color separation. And what we have today is Dolby 3D is an example of color separation. This is based on sending different wavelengths of light for each eye. Unfortunately, it's not compatible with 3-chip laser or 3-primary laser. It's the least efficient system by a significant margin. On a good day, you might get 10% efficiency from this system. But I think many people in this room would argue that it's also the system that gives you the best image quality, with the minimal crosstalk, the best, most faithful color reproduction. This would be the type of system you would use for color timing in post-production. So I think we've already seen a similar slide to this, the theory of color separation 3D from Barco, where you have different primary colors for each eye. For your left eye, you have a R1, G1, B1. For your right eye, you've got an R2, G2, B2. You need some sort of guard band between those two eyes so that the glasses can filter out the image that they're not supposed to see through that lens. Problem is, though, with broad spectrum white light, you need to filter the light first to get those primaries for each eye. And that's a really, really inefficient process. And that's why you're left with less than 10% of your light coming back to the viewer's eyes with this type of 3D system. So what if we could generate the separate sets of primaries right from the source? Of course, that's 6-primary laser. So let's go back to this slide here. I showed you this already, except I added that little sad face on there. Because now we've got a projector with 3 primary that's got all kinds of brightness, but it doesn't work with that color separation-based 3D. Now enter 6-primary laser. Here's where you see the huge benefits. Our system, with the dual projection heads, is 42 to 45% efficient. So think about that versus the most efficient system available today for xenon. This is almost twice as efficient as the best solution today. And it's based on color separation, Dolby 3D. If you look at the glasses in your hand, you see that they're Dolby 3D glasses. So we have the best of both worlds here. Highest possible brightness systems. The glass is only 3D system. The 3D is built right into the projector because it's generating the primary colors right from the source. Stereo contrast ratio. This is how you measure ghosting. And what most people are used to seeing is about 100:1 stereo contrast ratio. With a 6-primary system and well-designed glasses from Dolby, we can achieve well over 1,001 stereo contrast ratio, which means the ghosting is virtually imperceptible. We've solved this problem. It's compatible with a white screen. So that means it's really, really good speckle performance, no hot spots, a uniform audience experience. Every seat is the best seat in the house. This is your premium 3D experience, and we're going to show it to you today. Before we do that, we're going to talk about our 6-piece system architecture. So we have a dual projection head system. Immediately, that gives you the benefit of simultaneous left and right eye images. No flashing between eyes, no flashing artifacts. That also means that all of our lasers are in operation 100% of the time. Now, that's important. We use a fiber-coupled architecture as well. Using a fiber-coupled architecture, you can see you have the laser modules are outside of the projection heads. This gives you a system that's scalable. So if you want to select the number of lumens for your system, you can go from 10,000 to 20,000, all the way up to 120,000 lumens in your system. More than enough lumens for even the largest screen to achieve 14-foot Lamberts on a very low-gain white screen. A system like this would be upgradable. If you came along in 5 years' time and you had some great new laser primaries you wanted to add to your system, that's great. Throw them in the rack, hook up your fiber, you're good to go. Cooling is built into our laser modules. So each one of those modules has its own pump, compressor, liquid cooling system to keep only the right amount of cooling required for that box there. Plus, it gives you redundancy. If for some reason one of those modules goes dark, there could be 10 more in your rack that are still operating. Finally, it gives you the option of having a remoteable light source, if that's even a word. What that means in a nutshell is all the heat and the noise that's coming from the illumination source is now outside of the projector. You could put it in a different room if you want. Think of the boothless cinema possibilities with this type of system. You could hang the projection head in a room like this, and you wouldn't hear it other than a small fan for cooling electronics and DMDs. There's an alternative approach, alternative 6-piece system architecture that's based on a single projector head. And with this type of system, you would have a sequential left and right eye images. That means you're flashing between eyes. Present the left eye, flash between the left and right eye images. So this means that your lasers, your two sets of primaries, are only operating at a 50% duty cycle or less. So you're flashing your left eye lasers, and you're flashing your right eye lasers. So a 60,000 lumen projector with this type of architecture is only putting out less than 30,000 lumens for 3D. But 3D is the problem we're trying to solve here. It's not a 2D problem in cinema. It's a 3D problem that we're trying to solve with laser projection. So if you had an apples-to-apples comparison, if you wanted to do a lumen-to-lumen comparison, a system like this with a single head would cost almost twice as much as a dual-head system because the lasers are the lion's share of the cost in a laser projection system. A system like this has built-in lasers. This means it's not scalable or upgradable. All the heat and noise is still in the projection head. And having an external chiller unit offers a single point of failure. That chiller unit goes down, the whole system goes down. With that, we're going to move on to the demonstration. So our system in the back of the room there, you see it's the two highest projectors on the stand there. Our system has a 3001 contrast ratio. The screen in front of you is a 27-foot screen. I think it's actually slightly less than unity gain, so it's probably 0.8, 0.9 gain. You'll see the Dolby 3D glasses in your hand. We've got about 15,000 lumens, which is what we needed to get this screen lit up to 14-foot Lamberts. We've got some great content to show you. We've got a trailer from Frozen that's courtesy of Disney, and it's been color timed for 14-foot Lamberts. We've got the trailer from The Hobbit, too, in high frame rates, so that's a real treat, and that's courtesy of Warner Brothers and Park Road Post. And then we have a 5-minute clip from Avatar. They took it out of the vault and recolor timed this for us. Lightstorm Entertainment took this, recolor timed it for us at 14-foot Lamberts, and it looks fabulous. With that, we're going to roll the clips. We'll bring down the lights, put on your glasses. I hope you enjoy the demo.
choose your Ikran. This you must feel inside. If he also chooses, you move quick like I showed. You will have one chance, Sheikh.
How will I know if he chooses me?
He will try to kill you.
Outstanding.
Sansiu! Dokuratsi Sansiu! Zakenratsi!
Let's dance.
Tidak puskau. Operatsi Sansiu!
Make the bond! Jake! Sahilu, Jake! Sahilu! Srani.
That's right. You're mine.
First flight seals the bond. You cannot wait. Think, fly!
Fly?
Shut up and fly straight!
That's it.
Bank left! Level out!
That's it.
Summer in the city of Arendelle.
short of your enormity, O Smaug, the stupendous. We are the dwarves of Erebor. We have come to reclaim our home. There is no king in the mountains. We've been blind in our blindness.
Yeah, that's pretty real. Thanks for that, Don. Does my heart good. So now we'll open the floor up to, for questions. Please use the microphones in the audience and state your name and affiliation before asking your question. I'll get the ball rolling with the first question, one that's on the minds of everyone here in the industry. All three of you have presented new commercial products: an integrated laser projector with 6 primary 3D in the case of Barco, blue laser pumped phosphor cinema projector, and a modular dual projector 6 primary 3D system. So given that we're finally in the era of commercialization, what are the decision drivers for laser buyers this year, and how many systems do you expect the industry to install in 2014? And I'll open that up to anyone who wants to hazard an answer.
I'll start. Certainly, Christie has laser projectors that are in production now. We intend to ship several dozen systems this year, not only to cinemas, but also to Pro AV markets as well.
Okay. So you might have seen our announcements earlier this month or last month at CinemaCon. We already have commercial sales that amount to, I don't know, probably 15 laser projectors to be installed this year still, and we're also planning to roll out our system. Okay, it's back online. Similar numbers.
Well, from NAC side, we anticipate a few hundred units, at least, of the new laser phosphor system. So, I mean, we plan on attacking the market, North America, South America, pretty heavily with it, and we think we did a pretty good showing at CinemaCon, so we feel confident there will be a few hundred units sold this year.
So it sounds like we may be looking at 250, maybe 300 laser projectors sold this year. Any comments on the decision drivers? What are your customers telling you as their rationale for being not even early adopters, pioneers, I guess? We're still in that stage. Any comments on what's driving the purchasing decisions?
If I can go first, our customers are driven by several things. For them, it's a question of marketing as one. Being the first one around the block that installs a laser projector is of huge value to some customers. But that's not the only thing. Of course, the promise of high brightness, more efficient 3D and so on is what our customers are after. And they're also very much impressed by the total cost of ownership calculation and potential of savings, not only in electricity and lamps and so on, but also having a single projector. And we can go on for hours to debate this, but we'll see how the market reacts to that. Our customers are really impressed by our ability to do a single projector 6P on top of having this speckled system that also works on a silver screen.
Okay. We got some questions lined up. Let's start with Chris from Insight Media.
Guys, tell me, I mean, there's been some talk about going to the 2020 color gamut. So tell me how the current laser projection architectures might be able to get you there, or what you might have to do to get to a 2020 color gamut.
I'll just take that a little bit first, and I'm probably, if anything, at a disadvantage just because it's blue laser phosphor. So the color space that's existing now that we can achieve is realistically the DCI spec as it is. So direct RGB laser is going to definitely have that better chance with that. So, I mean, as of this moment, that's as of this moment. Obviously, engineering research will get it better and we'll be able to achieve a higher color gamut. But right now, we're just at that DCI spec, and that's where it's going to sit.
So we're slightly above the DCI spec in terms of color gamut, and it's more about selection of laser primaries right now. You have to keep in mind with a 6 primary system, you also have to be concerned with the guard band, the 20 nanometer separation that you have to keep between the left and the right eyes. So that somewhat limits your freedom to select the color primaries where you need to. I think the first dragon that we're trying to slay here, though, is brightness. And that means selecting primaries that have the highest photopic efficiency, which is what we've done with our system.
We think that the selection of the Rec 2020 gamut being, almost identical to a single primary laser is a bit unfortunate, because if you would really want to match the Rec 2020 gamut with a laser-based projector, then you will have so much speckle on screen that it will be unwatchable. So what we're really looking after is a second step of Rec 2020, which is actually more realistic, which provides tolerances on the primaries that will actually give the exhibition a wide color gamut, not necessarily the pure primary 3P Rec 2020, but something that's despeckled to a certain, to good extent to be watchable. So it's not, again, the primaries that are selected for Rec 2020 are available. You can make a projector out of them, but it's not going to be useful for anything else than lab purposes.
Is it realistic to think about going beyond 6 primaries, 8 primaries to achieve it?
To achieve the Rec 2020 gamut?
Yes.
Yeah, if you probably have more primaries that will average out on those points, yes. Then again, the question is, what is the efficiency of these colors, of this of the lasers, and photopic efficiency in terms of luminous output, and it's also a question of providing the wavelength. So I think there's still a lot of research to be done on the laser supplier side to bring this forward.
Okay, Bob.
Yeah. So just a couple comment on what was in 2 of the presentations. The 7-foot Lambert spec, the recommendation, when we voted for that, specifically was targeted at existing xenon projectors in the field, not at all intended to be a go-forward standard for 3D brightness. As I said in the previous session, we strongly believe that any laser installation that does not support 14-foot Lambert 3D presentation is misdesigned and not fitting the application. And we believe that that is a minimum requirement for any laser installation.
Well, there's some strong feedback from the industry, and tough to argue with anyone who's, you know, I mean, you've all seen 14-foot Lambert's 3D now, and it's certainly compelling. Another expert speaks. Wendy, your question.
Hi, excuse me, Wendy Ellsworth, Warner Brothers. I'm a bit confused about lasers on silver screens. I think many of us had hoped that lasers could provide enough brightness that we wouldn't need silver screens anymore. So could somebody explain that?
I guess I'm not following completely what you're saying, Wendy, but I don't necessarily think any one of us up here was promoting silver screens. I know in my speech, at least, what I tried to portray was that using the silver screen in the blue laser with phosphor, that you wouldn't get speckle, was the only thing that we actually talked about. So I don't recall any message really that we're using.
Oh, okay, then maybe I misunderstood the statement, because you know, silver screens have been used to help heighten the brightness, and I wasn't clear if your direction was to want to keep using silver screens.
Well, I think it's important to note that we saw 6 primary laser projectors talked about today, but you could also use polarized 3D with laser projectors just as well. So if somebody wanted to use a polarized system and they would need to have a silver screen to preserve that polarization, then lasers could still be applicable. I think the big news is you don't need to use silver screens with these 6P systems.
And let me just follow up. My comment on the 14-foot was on a white screen, not on a silver screen. So it's 14-foot Lambert's white screen to give the best consumer experience.
Could I ask you to clarify it one step further? A unity gain white screen?
Not necessarily.
Not necessarily. Okay.
Bob, does that mean DCI will be publishing a new specification to those terms?
I can't speak for DCI. I'm speaking for Paramount Pictures.
It's not for us. Sorry, it's not a question of promoting silver screens or not. We, as a projector manufacturer, can advise to exhibitors what is the best screen to use with a certain system. But on the other hand, there is also the economics at work for many exhibitors, and you know, having lower gain screens inevitably means putting a lot more money into your projection system. So yes, as an industry, we can say wide screens are better. They don't have a hot spot in the middle. They provide a better reflectance all over, and so on. But it's also a question of economics of the exhibitors and. You know, Dolby glasses versus polar glasses that cost a couple of dozen cents per glass is part of that economics as well. So we're not trying to influence that economics. We're just trying to say what is the best image experience for the viewers.
Okay, unfortunately, we're going to have to wrap it up here, but I'm sure the panelists will be happy to answer additional questions offline. Thank you all.
And thank all of you once again for coming today. It was a great day. Love seeing a large crowd at 9 a.m. in the morning, and we'll be back here again at 9 a.m. tomorrow morning to start on tomorrow's sessions. Tomorrow we will have the presentation from the people responsible for gravity. So looking forward to seeing all of you tomorrow.